Hello and welcome to Chapter 11.11 on Year 13 A-Level Mathematics Integration, Edexcel's course. So today we're going to look at, in particular, how exponentials can be used to model decay, for example, depreciation of a car, or even radioactive decay. And a big aspect of using exponentials to model real-life scenarios, especially exponential decay, is that radioactive materials decay exponentially. And so one of the primary applications of models, in particular exponential models, is to model radioactive decay across a range of different particles and isotopes. So I've thrown in an optional extra couple of worked examples at the end, which just illustrate on a deeper level the application to radioactive decay. So why don't Edexcel and other exam boards go into this deeper? The main reason is it's a maths course as such, and the applications can't be gone off into in much depth in any direction, because if that were to happen, the course would be, almost never ending. So that's left to the physics side, but I want to touch on it a bit because I feel it might be of benefit to the maths and physicists, and also the worked examples are relevant to the maths contained just within the course anyway. I'll stop rabbiting on and just show you the warm-up questions. So here they are, two to have a go at, because these two are rather big each one with multiple parts. So the first one, calculus, the pure side. Section 2 is mechanics. So pause the video here and try these on your own, and when you're ready to see the solutions, press play and we'll see if your solutions match my own. Okay, so assuming you've had a go, let's have a look together at the solution to warm-up question 1. So in warm-up question 1, we have this graph, a curve, modelled by y is 6 over e to the half x plus 4, where x is any real number. What we're asked to do here is to use the substitution u equals e to the half x to show that the area of R can be given by this integral, which is in terms of u, and a and b are constants to be determined. So what we're needing to do here is to transform this. The natural integral would be in terms of dx, because we're integrating y with respect to x. So we always start off with the basics. That's my suggestion anyway. So for 1a, the area R is going to be given by the integral from x being 0 is where it starts, and it ends with x being 2. So from x being 0, I'm going to know x specifically. X up to 2. The integral of y, which is 6 over a half x plus 4. So 6 all over e to the half x plus 4 with respect to x. Now we're instructed to use the substitution, so don't even think about using your own method. In fact, there's only one method you can use here, I think, which should be to use the substitution anyway, but we have to do exactly what the question says. So just probably say here at this point, let u equal e to the half x. So just introducing the fact we're making a substitution. You need to recall a necessary step now is to take the derivative of u to then get dx, the original derivative, in terms of the new one. So from here, if I take du by dx, differentiating an exponential, the power always stays locked, and only the constant part, if it's just a linear term in x, for example, it is a linear x, only the constant bit will come to the front. So this will just become half e to the 1/2 x. So then I can multiply, if you like, both sides of this by dx, and then divide by all of this. So du all over a half e to the 1/2 x. That's what dx is. So in other words, therefore, dx equals, because I'm taking du and dividing by half, that's essentially multiplying it by 2. So that's 2 lots of du all over e to the half x, but if we remember what e to the half x actually was, that's what we defined u to be in the first place. So 2 du over e to the half x is the same as 2 du just over u, because u is e to the half x. So that's the substitution we can now make. So I now know what dx is in terms of du. So dx I can now replace with this. And the rest I'll talk you through. So therefore the area is going to be the integral from when x is 0. Now this is something else we need to just consider. So for different limits, so when x is 0 and x is 2, these are going to change. So a fairly safe way of doing this would be to just do a table for x values and then relate those to u values. And we're considering, of course, firstly, when x is 0. So when x is 0, this is going to be e to the power half of 0. Half of 0 is 0. E to the 0 would just be 1. Then when x is up here 2, e to the power half x becomes e to the half of 2. Half of 2 is 1, so that's just e to the 1, which is e. So the limits of x equals 0, that codes to a limit of u being equal to 1. So in other words, a is u. And then x equals 2 codes to u being equal to e. So again, the b bit here is e. So these are just equivalent limits. So the equivalent limit of x being equal to 0 is u being equal to, so I mean to say 1, I should say 1, my bad. And secondly, the limit of x being equal to 2, that relates to when u is equal to e. Just didn't mean to put that colour on at that point. The colour needs to be blue. Okay, so just step by step, I'm doing it in a fairly slow way so you can see exactly where everything comes from. So this is going to be 6 e to the half x. Well, we said that's going to be u, and so that then becomes u plus 4 because that is u, and then dx is actually 2 du all over u. So now we can just simplify this. So in other words, the area R is the integral of 6 on the top. Now u plus 4, imagine in brackets, multiplied by another u, I can write like as u brackets u plus 4, so I'm just writing it exactly as what needs to be shown. Then times by 2, 6 times 2 becomes 12. In fact, we'll just do this in one step, because why not? You know, why make it longer, really? And that's then du. So we've shown exactly what we needed to. That's matched what the target was. So now, part B is just essentially performing this integration. So all we need to do now is actually just work this one out. So the area A, area R rather, this is going to be having to be partial fractions. So the first step, what we need to do, is just to split this into partials. So 12 over u brackets u plus 4, I'm going to set that equal to A over u plus b over u plus 4. We can then multiply all of this by all of this denominator. So that makes it 12. This fraction multiplied by u and u plus 4, multiplying this by u would cancel the on the bottom, leaving a brackets u plus 4. And in the same way over here, the u plus 4 would cancel we're just left with b multiplied by u. So let's just pick different values of u so we can work out the value of the letters. So I'm going to pick, first of all, let u be equal to 0. So if u is 0, what we get now is 12 equals a multiplied by 4 plus b times nothing, which is obviously nothing. So if 12 is 4a, 1a dividing both sides by 4, a has to be 3. In a similar way, what I can now do is try to work out what the other one is. So to work out b, I'm going to pick u being minus 4, because that will make this bracket become 0, then I can not have to worry about what a is. So now, if I pick u being minus 4, that now says 12 equals b times minus 4, because all of this becomes 0, so 12 equals minus 4b, so therefore b has to be 12 divided by 4, which again gives negative 3. So therefore 12 over u brackets u plus 4, that equals a, which is 3 over u, plus minus 3. So I'm just going to write minus 3 over u plus 4. So that's what we're going to integrate. So I just need a bit more space here. I'm going to extend the page. So area R, we're integrating from the top limit being e, the lower limit being 1. And obviously it was originally 12 u plus 4 with respect to u. But now we've got this in partial fractions. That's one and the same as 3 over u minus 3 over u plus 4, all with respect to u. We'll put this in brackets as well, in between e and 1. The key thing here is to note that the derivative of u would just be 1, and so the numerator is triple the derivative of this denominator. Similar thing here. Derivative of u plus 4 is just 1, and the top is triple the derivative of the denominator, therefore. So because of that fact, we can write these in terms of natural logs. So that's going to give us, when we integrate it, we're going to get 3 lots of ln of u, well, mod u I should say, minus 3 lots of ln of u plus 4, like so. Now, what you might want to do, if you really wanted to, is to make this into just one single log, using the laws of logs, and you can do that, in fact. If you really want to, you can factorize out the 3. I'm going to choose to leave the 3 in there. So, because we've got ln of one thing minus ln of the other, both have got a factor of 3 in them, so I can just put that 3 here. That's the same as ln mod of the first thing divided by the one I'm taking away here, over here. So it's u over u plus 4, it becomes. So now you can just put in the limits and actually work out what this is. So that's going to give me, first of all, for the higher limit is 3 ln, u is e, the bottom is e plus 4. Then the lower limit of 1 minus 3 ln. I don't need to put mods in because I know this is going to be positive, by the way. So when u is 1, that becomes 1 over 1 plus 4, which is 5. So minus 3 ln of 1/5. Then using the laws of logs, I can factorize out the 3 and write 3. And then ln of one thing minus ln of the other. Like I mentioned before, that's the same as ln of that one thing divided by the other. So that becomes e over e plus 4, all of that divided by 1/5. But again, this goes back to GCSE in a way. If you're dividing by 1/5, remember keep, change, flip. That's the same as multiplying by 5. So this thing here, instead of writing it as a dividing by 1/5, I can take this fraction and just multiply it by 5. And that's our result. So the area is 3 lots of ln, in brackets, this times 5, which is 5e, all over e plus 4. And that's question 1 complete. So I'll just do the double underlined red lines. Let's have a look at the second one, warm-up question 2. So, mechanics, and almost always mechanics questions are lots and lots of information. This is no exception. So, this one, at time t equals 0, a small ball is projected vertically upwards with speed u meters per second from a point A that's 16.8 meters above horizontal ground. So at this point, I'd be thinking a good idea would be to start to sketch this out. So if that's my horizontal ground, books tend to do this. Well, old-fashioned ones did anyway. That like denotes for underground and that's for surface. So if a ball's thrown from somewhere which is above ground level, so if I just make a little mark like so, and then we can denote the actual height that it's thrown from. So it's 16.8 meters above horizontal ground. Great. So I'll highlight in that we know that to be 16.8. So I'll just do a little full stop, which will be the ball. And it's projected vertical upwards. So again, I'm going to do an up arrow to denote the direction. And then I'm going to imagine, obviously it goes up, dot, 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 dot. I know if you're thinking, well, strictly this wouldn't be vertical, it'd be angled to come down over here. It should be crawling straight back down. But then you wouldn't see what I'm trying to get at, which is you have to go up, then you have to see and imagine it coming back down. Crash, hits there. So this here is going to be with a speed u, so that can be labelled as u here, meters per second going up. Let's see what else we have here. So the speed of a ball at the instant immediately before it hits the ground for its first time is 19 meters per second. The ball hits the ground for the first time at time t equals t. So this is when the time is 0 to begin with. Over here, that's where time is equal to t. If anything, I'm maybe over-labelling this, but you know what, let's try it. That's where t is t, where it ends up, and that final speed is 19. When it hits the ground for the first time, it's then going at 19 meters per second. So the motion of a ball from the instant it's projected until the instant just before it hits the ground for the first time is modelled as a particle moving freely under gravity. So this means SUVAT. It's constant acceleration of 10 meters per second. So acceleration due to gravity acts downwards, otherwise you'll be floating off into space, which would be fairly tragic and also very scary. So down arrows, 10 meters per second. So we need to show that u is equal to 5. Well, okay, it's SUVAT, so let's apply the SUVAT rules. Just give myself some space here. So I'll do part A at the top. So S-U-V-A-T. What do we want? What do we know? So we want to show that u is 5. Okay, well, that's fairly clear cut. So I'm interested here in working out what u is, the initial speed. Whoops, I used the wrong colour there. U I did in green initially, so let's stick with my own colour scheme, otherwise I'd be a hypocrite. So I'm interested in working out what u is. So I can call that x, I can call it question mark if you must, whatever. Leave it as u, to be fair. I know that when it hits the ground for the first time it's 19 meters per second, that's how fast it's travelling. However, I need to take a direction to be positive as a basically a consensus, really. So convention is a word I'm looking for. So my convention is I take positive to be the initial direction of travel. Initially, this ball is going upwards, so I'm taking up to be my positive direction. And that's one of the worst up arrows I've ever drawn. Anyway, so up is positive. So because this is going 19 meters per second going down, the final velocity with my convention is going to be minus 19. It's 19 meters per second in the negative direction. Acceleration due to gravity is at a size of 10, but again, it's acting downwards, so A is minus 10. So what we're wanting to work out is, of course, U, and what we can also work out from the question is when it's hit the ground, it's fallen a height of 16.8 meters downwards. So again, S would be minus 16.8, the way I'm calling up positive. T, I don't know, and suppose I don't need to know it. So what I do need is an equation not involving T, so I can work out what U is. So which one of the Suvat formulae doesn't involve T? Leave a bit of thinking time. Okay. Well, hopefully you've stumbled upon V squared equals U squared plus 2AS, because that's one we're going to be using. That's the one that doesn't involve T. So again, if we take that and just fill in what we know, so we've got minus 19 for V squared. That equals U squared, what I'm trying to find, plus 2. Not left myself much space here. Why do I do this to myself? So silly. A is minus 10. And S minus 16.8. What a silly person I am. Minus 16.8. So let's just neaten this up, because let's face it, it does need to be neatened up. This is just ridiculous. So minus 19, square this out. You can do this on a calculator, of course. That gives 361 equals U squared, and then 2 times minus 10 times minus 16.8, that becomes positive 336. If I now subtract 336 from both sides, you should see that 25 is U squared. Therefore, quite clearly, square root both sides, U is equal to 5. Part B, find the value of T. Again, we can still use Suvat here. And we know more information now, so if anything, Part B is now easier due to Part A. So we can use whatever we want to really here. So for example, V minus 19, A was minus 10, U I've worked out and shown is 5, S minus 16.8. I want to work out the time, so I can use whatever equation I want to, which involves T and is a legitimate Suvat formula. So I'm just going to go for, because I think it's one of the easiest ones, V equals U plus AT. So just plugging everything in, V is minus 19, U is 5, then plus A, which is minus 10, multiplied by T, which we're trying to find. So just working this through, minus 5 from both sides, I get that minus 24 equals minus 10T. Should really call it capital T, to be fair. So then dividing through by minus 10, we can see that T must be 2.4 seconds. The last one, the last part of it, rather part C, what we need to do now is find the time from the instant when the ball is projected until the instant when it's 1.2 meters below A. Okay, so this here is much easier than what it sounds. When the ball's 1.2 meters below A, that just means the displacement is going to be minus 1.2. Everything else is unaffected. So using suvat here, the initial speed is still the same question. It's no different scenario, so u will still be 5. Acceleration is still just due to gravity. That's still going to be minus 10. V, now we're not concerned with. We don't know the final velocity, and we're not being asked it, so V we don't need. That can just go away. The time is what we're interested in. So again, if I just call that T or question mark, it's a bit crude calling it a question mark, but I've gone there. Anyway, never mind. I'll have to redeem myself somehow. And S, well, because it's 1.2 meters below A, that just means S is minus 1.2. So now, we just need the formula for that one, which doesn't involve or need V. And I swear, for some reason, exam boards prefer this one massively to the others. Once again, it's S equals ut plus a half at squared. So once again, it's just a case of plugging in the values. So S minus 1.2, that equals u multiplied by t. So I'm just going to call t, obviously t, so 5t, plus a half times a, that's going to be half times minus 10, which of course is minus 5. So that gives me minus 5 t squared. So if I rearrange this, I'm going to get 5t squared. I'm going to get it all onto the left-hand side, so add 5t squared to both sides. Subtract 5t from both sides would give me this equation, which I need to solve. So now I can use the ClassWiz. So if I just get this one here and go menu. If you want to, by the way, you could be old school and, you know, complete the square or something. You know, there's nothing stopping you. And if I go to equation / function, polynomial option degree 2, because highest power is squared, the squared term is 5, the x term, well, the t here is minus 5, and then I've got minus 1.2. Press equals again. So t is either 1.2 or t is negative 0.2. Obviously that root makes no sense, but we can write it down anyway, then we can explain why to reject it. So t equals minus 0.2 or 1.2. That's rejected because negative time in this case is nonsensical. So therefore t is 1.2 seconds. So now we've done the warm-up, let's have a look at the main body of the lesson, which is modelling with exponentials, essentially. So let's get straight into it. Modelling with differential equations. So like the book, I'm just going to get literally straight into it. Like I said earlier in the introduction, a massive application of modelling with differential equations is to actually use models, particularly exponential models, to model exponential decay when it comes to radioactive materials. So this has got lots of applications in physics, which I'll talk through later. But if you're just wanting to do the standard sort of application, I've got two worked examples. The first one's here. So this is actually exponential decay without saying it as such. So the rate of decay of a mass of a particular substance is modelled by this differential equation. dx over dt is minus 5 to x, t equal or greater than 0. So x is a mass of a substance measured in grams and t is a time measured in days. Given that x equals 60 and t is 0, that's our boundary condition, that's what it's called, we have to solve this differential equation giving x in terms of t, showing all steps. Okay, so let's have a go. So we've got here dx by dt is minus 5 over 2x. So what we'll need to do first is the technique of separating the variables. So just write down what we have first. Just copying out the question. So I need to have x on one side, anything to do with t on the other. So what I'm going to do on both sides is just simply divide through by x. And then afterwards, I'll multiply by dt. In fact, if I want to, I can do both steps at once. So times by dt and divide by dx. Why not just be a bit quicker with it? After performing those two steps, what we'd have, because we're dividing by an x, we're going to have 1 over x, dx stays as it is. On the other side, we just have minus 5 over 2, or would have done if we hadn't have times by dt. So over here, we get dt. The next thing now is to integrate both sides with respect to their respective variables. So integrate this side with respect to x, this side with respect to t. Integrating 1 over x is just going to go to the natural log of mod x. So ln of mod x. This will become minus 5 over 2. This is just a constant, so it's just going to become minus 5 over 2t plus c. Like so. So what we can now do is basically put both of these to the power e. So I can do e to the power ln x, essentially. It's going to make myself a bit more space. It's not the best straight line I've ever drawn. There we go, that's a bit better. So taking both of these sides, e to the power of both, e to the ln mod x gives mod x on its own. But because t is time, x is rather a mass, is going to be non-negative. So the mod of a mass will just be x. So x will equal e to the power of all of this. So minus 5 over 2t plus c. But I can use the laws of logs to rewrite this as e to the power c multiplied by e to the minus 5 over 2t. I can now substitute in the boundary conditions. So I know when x is 60, t must be 0. So if I sub this in, sub x is 0, so 60 when t is 0, just telling the examiner or the person marking it what we're doing. X, which is 60, is going to become e to the c multiplied by e, and if t is 0, it becomes just 0. In other words, 60 equals e to the c. Now, normally, we try and work out the constant of integration, but if I've worked out e to the c, we've got the first piece of the equation. So if that becomes 60, we've got our answer, x equals 60 e to the minus 5 over 2t. So I'll just colour code in what I've done there. I've used x is 60 when the time is 0. So therefore we have our model. So finally we can say therefore t equals e to the c, which we've just proven is 60. So t equals 60 e to the power minus 5 over 2t. We can now consider part B. Now we've got our model, we can apply it to generate our solution to part B. So next, part B says, find the time taken for the mass of a substance to decay from 60 grams to 20 grams. Give your answer to the nearest minute. Well, this one, it starts off at 60 grams when time is 0. So this is actually easier than what it would seem. I can just work out the time it takes to get down to 20 grams. And the difference will just be the answer, because that time minus t equals 0 will just be my answer to how long it's taken to get down to 20 grams. So for part B, all we need to do actually is just to substitute in when x rather is equal to 20, because x is the mass. So if we sub x equals 20 into our model, what we're going to get is x, which is 20, days. Sorry, that should say an x. I apologise, that should say an x, my bad. So if x equals 20, then x, which is 20, will equal 60 e to the minus 5 over 2t. Divide both sides by 20, gives me 20 over 60, or 1/3, equals e to the minus 5 over 2t. Now I can take natural logs of both sides. So ln of 1/3 will equal ln e to the minus 5 over 2t. But if I do that, then the whole of the power will come to the front. So I just get minus 5 over 2t. And therefore t will just be ln of 1/3 divided by minus 5 over 2. And it does say we need our answer to the nearest minute. Currently, time is measured in days. So just bear this in mind before we jump to conclusions and write this down as our final answer. So the top of this fraction is ln of 1/3. So I'm just going to type this in as it looks. So ln 1/3 all over minus 5 over 2. That gives an answer of 0.439444, which of course is in days. So then, to change to minutes, yeah, we need minutes. Well, we need to work out how many minutes is in a day, essentially. So there's 60 minutes in an hour, and 24 of those hours in each day. So I need to times by 24 and times by 60 to convert it into minutes. Then I can round to the nearest minute. So that many days times by 24 must mean this many hours, times by 60 must mean this many minutes. 632.8 to the nearest minute is 633. To the nearest minute, at least. And that's worked example question 1 done for us. Let's have a look at worked example 2 then. So for second one, we've got a biologist who's conducting an experiment to investigate the growth of mold on a slice of bread. They've measured the surface area of bread, A, cm squared, covered in mold at times across t days after the start of the experiment. Initially, 9 cm squared of bread was covered by mold, and 6 days later, 56.25 centimeters squared of the bread was covered by mold. In this model, the rate of increase of the surface area of bread covered by mold at any time t days is proportional to the square of a root of that area. So by forming and solving a differential equation, show that the biologist's model leads to this equation here, A equals 3/4 t plus 3 squared. All right, so one of the key bits of information is this bit here. It says a biologist's model for rate of increase of the surface area, I'll highlight this in fact, for rate of increase of the surface area of bread covered by mold anytime t is proportional to the square root of that area. So the rate of increase of surface area of bread, so this is going to be dA by dt, is what this is saying. Rate of increase of surface area of bread, that's going to be dA by dt. It's proportional to the square root of that area. So piecing this together, we have this equation of proportionality. So now in a way it takes us back to GCSE ever slightly. If one thing is proportional to the other, we can write it, replace this fish symbol, the proportionality symbol, with an equal sign. So dA by dt equals some constant k multiplied by the square root of a. So that's our way into doing it. It then says the boundary conditions as well. It says at 9 cm squared, is when it's the start of the experiment at time t equals 0. In 6 days, we've got that area covered. So what we're going to do first of all is to separate the variables. So if I divide both sides of this by root a, and as well as that, we're going to do another move. We're going to multiply by dt as well. So if we do the same steps to both sides, both dividing by root a and timesing by dt, this here will transform into dA over root a equals, on the other side, just simply k dt. I'm going to write root a, or 1 over root a, in power form because that's easier to integrate. So a, square root of a, is a to the 1/2. Because it's 1 over a to the half, I can write this as a to the minus 1/2. So I've got a to the minus of a half dA equals k dt. Now separate the variables, I can integrate both sides. So again, if I just do that, a to the minus half, if I increase the power by 1, becomes a to the positive 1/2. I then need to divide by that new power. So that's going to be dividing by 1/2, which is the same as multiplying by 2. So that's going to give me 2 lots of a to the 1/2. It's just going to be k integrated with respect to time, which is k multiplied by t, plus c, of course, where c is some constant of integration. So now if I rearrange this by dividing both sides by 2, I see that a to the 1/2 equals kt plus c, all divided by 2. That's a to the half, but I want to have a, so I can square both sides. So a to the power half squared gives us just a, and this all squared will of course give us kt plus c all over 2 squared. Well, we now know when time is 0, a is 9. So initially 9 cm squared was covered in mould. So let's substitute this in. So sub t equals 0, a is 9. That'll then give us some more information to use. So t is 0 and a is 9. This now becomes 9 equals, kt will vanish because k times 0 is 0, so just leaves me with c over 2 all squared. Well, obviously c over 2 would have to be 3 because 3 squared works and gives us 9. So c over 2 must be 3, therefore c equals 6. But we also need to work out the constant k. Luckily for us, we have another boundary condition, which is 6 days later, in other words when t is 6, 52 centimetres squared of bread is covered by mould. So we can now substitute this in. So now if I sub in t is 6, and the area is 56.26, so 56.25. Sorry, I seem to be going slightly mad. This will tell us what k is essentially. So next up, plugging those values in, and now we know that c is 6. The area, which is 56.26, equals k times t. So t is 6. So k times 6 is 6 lots of k, plus c, which I know now is 6, all over 2 squared. If I square root both sides of this, I can work out what is inside the brackets. Now if I square root 56.25, you can try this on your own, that gives me 7.5. So 7.5 will equal 6k plus 6 all over 2. When you get off space slightly here. So 15 equals 6k plus 6. Take away 6, then divide by 6. Hopefully you'll see that therefore k equals 1.5. So I've got the important ingredients. I know that c is 6. I've just worked out that k is 1.5. So now we can finish this question off and actually fill in what the full model is. So therefore, A, which is the area, equals K, which we know is 1.5, T plus C, which is 6, all over 2, squared. And just let's write it in this exact form, because when we've really shown the examiner, we know precisely what was needed of us. 1.5 divided by 2 is 0.75, which as a fraction is 3/4, so it does work out to be correct, as you'd expect. I get 3/4 of a t, and 6 over 2 gives us this plus 3 constant within the bracket. So we've got 3/4 t plus 3, all squared, as was required to be shown. Now, for part B, it says the biologist's full set of results are shown in this table below. So 9 and 56.25, that was mentioned in the actual wording of the question. Time goes on and the mould increases in area. But what we need to do here is to use the last 4 results in the table to evaluate the validity of this biologist's model and to offer a possible explanation of their results. So what I'd suggest you might want to do here is to do like an extra row yourself underneath these 2 rows in the table, so you can actually compare what the model says, this, compared to the actual area which was observed. So if I fill in for different times of t, what 3/4 t plus 3 all squared is, what the model of the area gives us, we can then compare with the actual. So I've pre-done this just for speed and just being a bit more fluent. So when time is 0, that gives 0 plus 3 all squared, which of course is 9, which it told us. When time is 6, plug in 6 into this bracket and square, you should find it's 56.25. You try these calculations on your own at home or in class if you're listening. If you plug in when t is 12, now it's not quite the same, but it's still a very, very good approximation. It's almost perfect. But if you notice here, the area of the bread covered in mould is actually a tiny bit less from what my models predicted. So it was exactly the same. Now it's going a bit underneath what the model would say it should be. This one again, still very good, but now it's fallen more than a unit off, but still a very, very good approximation. So it's still an excellent approximation up to 18 days even. If I go to 24 days though, not that it's a terrible approximation, but it's obviously nowhere near as good as it was before. So it's going worse, and when time goes to 30, then it's much worse. We're talking almost a difference of 50% between these two. So this is a huge difference, whereas it started off being really, really accurate. So to fully evaluate the model, it's not just a case of saying it's either right or wrong. We need to deduce and show that we understand. Up to the time point of 18 seconds, this model is very, very good indeed. However, it falls off and becomes less accurate after the point of 18 seconds. And we need to offer a possible explanation of that. So essentially, there might be some limiting factor which is stopping the mould from growing indefinitely. I would suggest to actually picture this scenario in your head, as disgusting as it might sound, imagining bread rotting. But it's talking about here, surface area of bread. If you imagine a slice of bread, essentially. Okay, so you've got your loaf. Of course, it's like a brown colour, so brown. Possibly the least appetizing looking bit of bread in your life, this. Anyway, I might just abandon this is awful. Anyway, so the bread, as you can see, it's got a finite area. The point I'm making with that is, after a certain point, there's no more fresh bread to turn mouldy. So it'll get to a certain point, the area, where the area here will just stop, and that's when all the breads become mouldy. So that would be an explanation of what the limiting factor could be. So in terms of wording it, I'd suggest we want to put something like this. Essentially, the model is very accurate up to the point of 18 days, but beyond this, the actual amount of mould falls further and further below the amount predicted by the model. This may be due to a limiting factor. If you're not sure what the limiting factor is, put your full stop there and don't worry about going too far or like saying something too silly. But if you are feeling a bit brave, I think this is a fairly good, realistic limiting factor. It's probably the lack of fresh bread still left available to turn mouldy has gone so low that the amount of mould itself has to just stop increasing after a certain point. Anyway, that's the second worked example. The next two are going to talk specifically about radioactive decay. So at this point, you can now politely sort of turn off and just do the suggested exercises. Or if you want to listen on, please do. So these next two and the introduction to them are going to be talking strictly about radioactive decay. So without further ado, let's have a look at questions 3 and 4 of these worked examples. As it says, optional extension, radioactive decay. So a bit more background, a bit more explanation for you. Some chemical elements exist in what are called isotopes, different forms called isotopes, and that's because of having different numbers of neutrons in their nuclei. That's just joule of nucleus. So while many isotopes are stable, some are unstable, and these are called radioactive. And that's owing to their particular combination of protons and neutrons rendering the nucleus with excess energy, which then has to be expended through radiation. Such isotopes are called radioisotopes. A really crucial one for us is carbon-14. Carbon-12 is the stable one. Carbon-14 is an unstable radioisotope, which goes through radioactive decay. It decays quite slowly. It's not like, say, plutonium or something like that, but it does decay very slowly, and it is therefore a radioisotope. Across a set time duration, so it might be, for example, 1 second, any one atom of a radioisotope has a statistical probability of decaying. However, because that probability of any one individual atom you're looking at decaying within, say, the next 1 second is virtually zero in most cases, you can't really meaningfully apply that probability to small numbers of atoms, and certainly not just one individual one. You'd be waiting for absolutely forever, unless it was like a 1 in a billion chance or something like that. So applying the statistical model to a small number of atoms is similar in a way to, trying to do some probability analysis by just buying 2 or 3 Euromillions tickets. You wouldn't get anywhere because the probabilities are so shrinkingly small. To balance it back out, if you like, you'd need to have lots and lots of lottery tickets, or in our case, lots and lots of atoms, to make any meaningful statistical analysis viable. But we can do that because even just 1 gram of carbon-14 contains in the region of 5 times 10 to the 22 atoms. So we can apply probability meaningfully across huge numbers of atoms, and from that we can then model very accurately the decay of a sample mathematically. So this is a key concept now. If you were to double, for example, the sample size of a radioactive sample, you'd rightly expect to observe double the number of decays per that same time frame, because you have double the number of radioactive particles that might decay. So the decay rate might go from 50 decays per second to, say, 100 decays per second. If you were to multiply the sample size by 10, you'd expect the rate to increase by 10. So what I'm driving at is essentially the rate of radioactive decay is proportional to the number of current radioactive particles in that sample at any given current time. Using that concept, let's have a look at worked example 3. So worked example 3 begins where the explanation ended. It begins by saying radioactive decay, and in fairness it should say the rate of radioactive decay is proportional to the number of radioactive particles n present in a sample of radioactive material. So part A, we just need to establish clearly and logically why the rate of decay, dn by t dt, is minus lambda t, explaining why lambda is a positive constant. So first of all, because it says about proportionality, let's start with the basics. So again, imagine it says the rate of radioactive decay proportional to the number of particles present. So from that, like we would do at GCSE, would say dn by dt proportional, that fish-looking symbol, to the number of particles. So what we're going to say now is dn by dt equals some constant multiplied by n. I'm going to call the constant not k or lambda, but actually a minus lambda, then the n. So now we can explain why. So we need lambda to be positive such that minus lambda is therefore obviously going to be negative. So minus lambda, and that will make dn by dt less than 0. So that dn by dt is less than 0 for all t. And this is required because we're talking about decay. Since we're talking decay. So decay means it's going to be going downwards. Negative rate of change. So that would suffice for A. Now, part B. So part B, using information from part A. So part A, we ended up with dn by dt equals minus lambda multiplied by n. But it also says at time t equals 0, n is n0. So we can substitute that in. So if I in fact, no, what am I playing at? Let's first of all actually get this into this particular form. So what I'd like to do now is to see if we can get this result. This now is what we need to do, is to separate the variables. So I need n's on one side, anything to do with t on the other. So I'm going to divide through by n and multiply by dt. So I'm going to get 1 over n dn on the left, and on the right it's going to become minus lambda dt. I can now integrate both sides, the left with respect to n, the right with respect to t. So performing the integral, this becomes ln mod n on that side. On the other side, integrating minus lambda, which is just constant with respect to time, gives minus lambda t. And of course we have a constant of integration plus c. If I now take both of these terms raised to the power e to the power ln mod n, I'll just give me mod n, but I can call that just n because n is a number of particles which is going to be non-negative always. To have a negative number of particles is going to be meaningless. So this is going to give n, and over on the right hand side we're going to have e to the power minus lambda t plus c, and using the laws of logs I'm going to rewrite that as e to the c multiplied by e to the minus lambda t. Now I can actually substitute in this condition at time t equals 0, n equals n0. So sub this in. At t equals 0, n equals n0. So n is n0 at t equals 0. That's going to give us e to the c multiplied by e to the minus lambda t. But if t is 0, that's just going to be e to the minus 0, which is just e to the 0, which is 1. Therefore, n0 is e to the c. Or I can just put it the other way around. E to the c is n subscript 0. And so the constant, the unknown part of this equation we now know. I now know that EC is n subscript 0, so I've got my full model. Therefore, part B is done. So conclude by saying this. So n subscript t, the number of atoms at any particular time t, is given by the number of atoms at time 0 e to the c, which is n0, multiplied by e to the minus lambda t. And that is the general form of a model for exponential decay. Now, lambda itself has particular significance. So let's talk about the significance of lambda now. So in the equation we've just generated, n subscript t equals n0 e to the minus lambda t. The constant lambda is known as the decay constant. Another constant, which you've probably no doubt heard about, is a radioactive material's half-life. And the half-life of a radioactive material is defined as the time taken for the original amount of radioactive material to have halved in mass. In other words, how long does it need to live until it becomes half its original size? So it's a strange phrase, half-life, but it does actually make sense. So let's have a look at a worked example on this in 3 different parts. Worked example 4. Using this equation, let's show that the half-life, which is given by t subscript 1/2, is given by t to the power 1/2 is ln2 all over lambda. So 3 different sections for A, B and C. So first of all, A. The definition of the half-life is the time after which the mass is halved. And so, at the half-life time, the mass at that time, the number of particles at the half-life, has become half of the original particle. So it's become half of n subscript 0. So what we can do now is sub in when time is at the half-life. So using this equation, nt becomes half NO, so at half-life, same as number of particles, half of the number of particles at the beginning, and of course we've got this equation, NO e to the minus lambda t. So we're just focusing in on this bit now. So that bit's just there for, you know, for flavour, if you like. That's just showing that I'm talking about the number of particles at the half-life. So the number of particles at half-life is half of the original number of particles, and that's the general form for any time. So this bit of the equation, we've got n subscript 0 on both sides. So we can essentially divide through both sides by n subscript 0, cancel them off if you like. So I get now a half equals e to the minus lambda t. That's a very bad t, I'm going to redraw it. If I now take logs of both sides, ln of 1/2 equals ln of e to the minus lambda t, which just gives minus lambda t. Now, ln of 1/2 is the same as minus ln of 2. If you think of ln of 1/2, I'll just doodle it here. Using laws of logs, that's the same as ln of 1 minus ln of 2. But ln of 1 is 0, so you just get minus ln 2. So I can rewrite this a bit simpler by just saying minus ln2 equals minus lambda. I should really say this is t to the 1/2 because I'm talking about half-life in particular. So minus ln2 equals minus lambda t subscript to half. Therefore, dividing both sides by minus lambda, so therefore I get that t subscript 1/2, the half-life of the substance, is minus ln2 divided by minus lambda. The minuses cancel, which just gives ln2 over lambda. And that's what we needed to show, so that's part A done. For B, we're given the half-life of carbon-14 as 5,730 years to the nearest decade. So knowing that, we need to find the decay constant, lambda, of carbon-14, giving our answer to 3 significant figures. So we can use this equation here. So t to the 1/2 equals ln2 over lambda, the decay constant. Rearranging this, the decay constant will be ln2 divided by the half-life of a particular substance we're talking about. The particular substance we're talking about here is carbon-14, and we're told the half-life of that is 5,730 years. So I can just substitute that in. So the decay constant for carbon-14 is going to be ln2 divided by 5,730. So again, get ready the old calculatrice. I think that's French for calculator. ln2 divided by 5730. That pops out to give us, to three different figures, 0, 0, 0, 0, well 0.000121. Obviously it goes on, this is only approximated, but this is what we want, because it says give your answer to three significant figures. So therefore, the full model for carbon, so for carbon-14, I've got that the number of particles at time t is number at time 0, e to the minus lambda t. But now we know the decay constant, lambda, is minus 0.000121 t. Next, some real-life history, actually. A wooden rescue ship was unearthed in Herculaneum, and this is a place in Italy, and this happened in 1984. A fragment of this ship was sampled. Historians and scientists established it was made from a type of tree native to Naples, which isn't too far away from Herculaneum, and that sample of ancient wood contained only 79.4% of the carbon-14 present in those same trees that are alive today, well, alive in that day, growing in Naples in 1984. So compared to the trees of a day, it only had 79.4% of the carbon you'd expect if it was cut from a living tree. So in other words, we can deduce between 1984, from when it was made until 1984, that long period of time, about 20-ish% of the carbon-14 had been decayed. So using that information, we can estimate to the nearest decade, in fact, quite accurately, the year in which the ship was constructed. So let's try it. So using our model in purple here, we can just proceed. So now n is only a certain proportion of the starting amount of radioactive particles. So it only contained 79.4% of the carbon-14, as those in Naples currently, well, in 1984. So in other words, currently, n at t is only 79.4% of the carbon you'd expect at time being 0 if it were cut in the day, 1984. As a decimal, 79.4% is 0.794. So we can say it in 1984, the number of particles at that time was 79.4% of the number of particles you'd expect when that ship was actually made fresh back in the day. So from this I've highlighted in green, we can deduce this. So from that, if I just sub in the NT is now this, I can sub in this expression for NT in place of n subscript t itself. So therefore 0.794 n subscript 0 equals n subscript 0 e to the minus lambda t, which is this number we arrived at in part B. So minus 0.123121 t. Of course here we can divide both sides by n subscript 0, so cancel them off essentially. Then take ln of both sides. So the next step, we're going to get ln of 0.794 equals ln of e to this power, which just brings the power to the front. So that's going to give us minus 0.000121t. So therefore, rearranging, t must be ln 0.794 divided by minus 0.000121. Let's see what that gives us. So ln 0.794, close brackets, all over, minus 0.0, oops, it's not a 0, is it? 0.000121. Oh, I forgot my minus sign as well. Minus, there we go. That gives, to the nearest year, 1906. So 1906 years ago. So therefore, must have been built 1906 years before 1984. So 1984 minus 1906 gives 78 AD. It does say the decade it was constructed. So in other words, it was built in the AD 70s. Bit of an extension for you if you really want to. I don't think you would do, but I hope you do. Consider what happened about this time period, about 78, 79 AD, in the town of Herculaneum in Italy. So that's over to you if you want to. If you don't, what I do suggest, or almost demand you do, I can't really demand, but you know, you should do it, being if you want a good A-level result, please try the questions yourself now. So if you go to page 328 and 329, that's exercise 11K in the beautiful blue book, year 13's. Try all the questions, and as I always say, keep checking them as you go through to make sure you're understanding the questions as you go, rather than trying them all and only realising at the end you've made the same mistake again and again. If you've stuck, please do ask for help. You should know how to reach me by now, and never give up. Keep going always. So from me, Mr. Bailey, it's goodbye for now.